I'm Dan from LMAX, and before Mark comes out for his talk, I want to talk to you briefly about an interesting problem that the two of us worked on at LMAX a few years ago. And when I'm talking about interesting problems, I like them to be quite broadly applicable, so rather than being something very LMAX specific, it's something with more general appeal. And it should also be interesting that it challenges you to really question the technology you're working with. And this certainly did that for me. There was actually one point when I ended up going up to Mark, who's my team lead at the time, saying, I don't understand how Java works. Which, given that this all happened just after I started working at LMAX, it probably didn't give him a great deal of confidence about my technical skills. Fortunately, though, my understanding of Java turned out to be vindicated, and it was quite an interesting journey to get to the solution. As I was saying, let's take a look at the problem that I was actually facing, which was this. An array index out of bounds exception on this line right here, an array copy, which in itself is not particularly unusual. Certainly an array copy can throw an array index out of bounds exception. And if we take a look at our variables, you can see that we've got a source buffer of 64 bytes, a destination buffer of 66 bytes. And between these buffers, we're attempting to copy about 1 billion bytes. So yeah, an array index out of bounds exception is actually what you would expect there. The interesting bit is when you take a look at these two lines and see where length is coming from. It's coming off this event, but there's also this other variable, total message length, which is derived from length and this constant size of int. And if we take a look at those values, you can see that the constant is 4 and total message length is 64. So we can tell that length must have been 60 at the time that this was evaluated. It's now 1 billion, but back then it must have been 60. Except that both of these variables are final, so that shouldn't really be possible. Hence the confusion I had. But let me give you a little bit of background about the application first. So what this is doing is it's reading a large journal from disk, and the bug was quite easy to reproduce. It would happen basically all the time. Always about 13 or 14,000 iterations into it, like 13 to 14,000 entries into the journal. It wouldn't always happen at the same point, though. So reading the same journal, sometimes it would be around 13,000, sometimes around 14,000. So it didn't seem to be just a bad entry in the journal. It was something else. And there were some other Buggy properties of this. Like anytime I tried to set a selective breakpoint to catch it before it happened, it would never happen. If I tried changing the code to add extra debugging, the problem would go away. The only way I could catch it was with the exception breakpoint that would show it after it had occurred. So it was kind of confusing. I went down some dead ends trying to figure it out, because there are actually some creative things you can do in Java to change the value of final variables, like you can do some things with reflection or using the unsafe, but we didn't appear to be doing any of that. But this was the point where I was thinking, maybe there's some other thing in Java that I don't really know about, which is why I went to Mark for help. And with him, we ended up looking into what the JVM was actually doing. So if you run your Java application with these parameters, then it will actually print out the assembly that the JVM is producing when it compiles the code. And with these, what we saw was that about 10,000 iterations in, it was printing out this assembly. Now, I don't assume that everybody is going to be fluent in assembly. Certainly, I'm not. And when we were going through this first time, we had like the Intel Developer's Handbook open on the other screen to figure out what was actually doing. There are some hints in here, like references to the code to make it a bit easier. But in a nutshell, basically what this is doing is, if this is the original program, what that was telling us is that it spotted that these two methods are being called a lot. And it's switched from interpreted to compiled mode, and it's applied some optimizations like inlining this too-big endian method. So if this is what those two methods look like in the original source, this is some kind of synthetic Java that represents what it would have looked like with the actual assembly that it was running. So you can see the too-big endian call has been inlined. So that's the most obvious optimization that it had applied. But there's another one which is a bit more subtle, which is its use of intrinsic functions. Now, I'm not sure if people are broadly familiar with intrinsics in Java. I hadn't actually come across them until I started working at LMAX. But in a nutshell, intrinsics are basically certain well-known parts of the Java API that the JVM knows can be executed in a highly optimized fashion. For example, here we have the reverse bytes method on java.lang.integer. We've got these 4 lines of Java, which translate to these 20 bytecodes, which in turn compile down to the following 27 lines of assembly. Except that reversing the bytes of an integer is actually quite a common operation. It's the endianness change. So Intel has actually provided an instruction to make that much more efficient. And the JVM knows about that. So when that code is running on an Intel architecture, the JVM sees a call to reverse bytes, and it knows not to compile these 27 machine instructions, to do this one single line using the bswap instruction. Now bswap, it takes this register and actually reverses the bytes on the register. And obviously, running one line of assembly, it's much faster than running those 27. And this is a particularly relevant example for the problem that we were facing, because if we go back to the code, you can see there is actually a call to integer.reverse bytes. And if we look at the assembly, you can see there is in fact a bswap in there. More conclusively, if we look at the debugger and we take this value of 1 billion that we had, length, and reverse it, you see the result is 60, which is the value that we were expecting. So this obviously has something to do with it, except at the point that this compilation was happening, nothing was actually broken. This happened about 10,000 iterations in, and the problem didn't occur until about 13 or 14,000 iterations. So this is showing us a little bit about what's going to be going wrong. But let's go back to the synthetic Java that I showed you earlier. So here you've got the reverse bytes call. And this is like I'm sort of simulating the effect of the bswap, where I said it's actually taking the value of the register and reversing the bytes. So it's mutating its operand. So it's effectively taking this value I and changing it, which in this case shouldn't really be possible because I is final. So if this was real Java, that wouldn't compile. But this is just the output of what the optimizer has produced. And in this case, although it's quite an aggressive optimization, it's permitted because there's nowhere else in this scope which is expecting the unreversed value of I, so it's OK for it to be changing it. And at this point, everything is working fine. But then a few thousand iterations later, the optimizer kicks in. And this is what we had after the first round of optimization, where we've got this the writeInt method down there. And what happens at the second round of optimization is it becomes a bit more aggressive, and it actually inlines this call of writeInt there. So it gives us something basically like that. And you can see it's kept the behavior of mutating the value that's being reversed, but before that was OK because it was restricted to the scope of that single method. But now that value is actually being used elsewhere here. It's being passed in what was expecting the unreversed form into the array copy method, which is what we saw the problem was coming from earlier. So this was how we ended up with a ridiculous value for length. So this turned out to be the cause of the problem. It was actually a bug in the optimizer in the JVM, which was not what I was expecting it to be when you first started looking at it. You don't normally go into problems thinking, oh, it's probably a JVM bug. But at this point, I was quite happy thinking, it's like, oh, the particular edge case of our application has flushed out this bug in the JVM. And we can fix it. It's open source. We can make the world a better place for everybody. We can have our code running on millions of machines around the world. Before we look into seeing exactly how it's broken, let's just make sure it's still broken on the latest version of Java. So we downloaded the latest version of Java and found out that it wasn't broken on the latest version. Somebody had already fixed it. So unfortunately, we didn't get to fix the world on that day. But it did turn out to be quite an interesting exploration to get to that solution.